So far, all the tests that we have learned applied only to series with positive terms. Well, not all series have positive terms, so now we need something else. We need tests for series that have some positive terms and some negative terms. We're starting with the very simplest case of that and saying, what if we just took one of our series that we know has all positive terms, and then in the numerator had -1 to the n? We've seen that before. -1 to the n for all odd powers would just make that fraction negative. For all even integers would make that term positive, and so our terms would be alternating, and that's called an alternating series. For example, n equals 0 to infinity of -1/2 to the n. That's just the geometric series 1/2 to the n, where every other term is negative. So that would be the very simplest example of an alternating series. It would be an alternating geometric series. And our test for geometric series, remember that test has absolute value of r in it. So actually, we have dealt with this series with some negative terms in it. Whatever the base is, you take the absolute value of that and compare it to 1 to see whether the series converges or diverges. So we have seen an alternating geometric series before, but it's the only series we've seen that had both positives and negatives in it. All right, so what do we know? The alternating series test. Let a sub n be the positive term. Then the series n equals 1 to infinity of -1 to the n times that positive term, and the series n equals 1 to the -1, try again, n equals 1 to infinity of -1 to the n plus 1 times a sub n converge when these two conditions are met. Now, before we even talk about the two conditions, what's the point of this? They're identical except for one has -1 to the n, one has -1 to the n plus 1. What difference is that going to make?
That changes whether every other term starts on the first term or on the second term.
Yeah, it just affects whether you start out with a positive and then go negative, positive, negative, positive, negative, positive, or this one, -1 to the n plus 1, would start out with the first term being what? Positive. Because n plus 1 would be an even number, and -1 to an even gives you a positive. So all that's really saying is it doesn't matter which terms, whether it's the even terms or the odd terms that are negative. These converge when the limit as n goes to infinity of the nth term of a sub n, disregarding the -1, just the limit as the nth term of a sub n is 0. What does that sound like a whole lot like? When else have we said something about the limit of the nth term is 0? The nth term test. And we have said when the limit of the nth term is 0, what does that tell you about the series? Nothing. The nth term test is actually when the nth term is not 0, what does that tell us? It diverges. So that's still true. When the limit of the nth term is not 0, then the series diverges. But when the limit of the nth term is 0, and we can prove that the series is decreasing, which we're just going to look at the graph. A sub n plus 1 is less than or equal to a sub n, means the series is decreasing after maybe the first few terms. Remember, it doesn't really matter if the first few terms are decreasing, as long as after some finite number n, it's decreasing forever after that. When those two conditions are met, this still doesn't tell you anything about whether a sub n converges or diverges, but it does tell you the alternate series converges. All right, so two things. If the limit of the nth term of the series a sub n, not these two, but just the a sub n, if that's 0 and the series is decreasing for all values of n except for possibly the first few, then our alternating series converges. All right. Determine the convergence or divergence of the series. This is an alternate series because of the -1 to the n plus 1. We're going to just look at whether the limit as n goes to infinity of the rest of the function without the alternating part, the n over 3n plus 2, we're going to see if that limit is 0. This is the a sub n right there. Is that limit 0?
No.
That limit's 1/3. What does that tell us? That tells us actually not only that this diverges, but just by the nth term test, it's telling us this one diverges also. So really we can say both this original guy and this a sub n without the alternating, what causes the alternating series, both of those diverge.
So proving one part technically proves the other.
Yeah, because if that was our whole series right there, if that's all we had with the summation in front of it, and we knew that the limit of that as n goes to infinity is not 0, then automatically we would know that diverges. That's just telling us, alternate series test is telling us, well, this diverges too. So both the a sub n and the -1 to the n plus 1 times a sub n, both of those diverge. All right. Let me just save ourselves a little bit of time. That's all we had to do on that problem. Once you know it diverges, you really don't care about whether the series is increasing or decreasing. But let me just say on other problems, you know how to look at the graph and tell if it's increasing or decreasing, and you'll do that on the test, right? Because you can't use the alternating series test, both parts of it, unless you've looked at the graph and said the alternating series test applies. But I can tell you that last night I graphed all of those, and just the a sub n part, all of them were decreasing. So I've already looked at the graph of these, and all of the series from n equals 1 to infinity of a sub n are decreasing. So we're not going to have to write that out on every single problem. All right. What about number 8? The limit as n goes to infinity of, without the alternating part, this would just be 1 over e to the n. And really that's the same thing as limit as n goes to infinity of 1 over e in parentheses to the n. I wrote it this way so that I could recognize it as what? A geometric series where the r, what about that r? It's less than 1. That's about 1/3. So that's less than 1. And what do we know about a geometric series that's less than 1? Where the r is less than 1. It converges. What's this limit?
0.
Yeah. So I'm going to say, so the alternating series converges. But look at the difference between what I wrote on number 6 and number 8. On number 6, if one of the series diverges, they both diverge. But you can't say that because the alternating series converges, this series converges. We're going to talk about that on the back side of this page of notes. But if one diverges, both diverge. It's not true. If both converge, one converges, then they both converge. If this was the original series that we were given, and we tried to apply the nth term test and found out the limit of the nth term is 0, would that have proven this converged? No, we'd still have to use some other test to see if that converged. We're just saying the alternating series converges. All right. What about the limit as n goes to infinity of n over n squared plus 5? What's that limit?
Zero.
You just use the rational zeros theorem on that. The degree of the denominator is higher than the degree of the denominator. That limit being 0 doesn't tell us that this series converges. It tells us the alternating series converges. And I made myself write that, not just the word converges, but I made myself write the alternating series converges because I didn't want to allow myself to get confused and think I was saying that this converges. I don't know anything about the series n over n squared plus 5. I only know something about the alternating series. All right. This is seeming easy enough. I'm wondering if we can skip some. Anything terribly exciting? What about 14? The limit as n goes to infinity of the series without the alternating part would just be n squared over n squared plus 4. What's that limit?
1.
What does that tell you? Yeah, both series diverge when that fails the nth term test. Oh, 18 is interesting because I don't see how it belongs in this section. It doesn't have the -1 to the something in parentheses to the either n or n plus 1. What's it doing here? This is cosine of whole pies. What is cosine of whole pi? Always. Either 1 or -1. That's where the alternating part comes in. So let's write this as an alternating series. Sum n equals 1 to infinity of 1 over n. But we've got to have that +1, -1 alternating sign. In order for this to be equivalent to the series in front of it, would that need to be n or n plus 1 in the exponent? I would just say, I don't know, let's try n. If I let x be just n, then when n equals 1, I'd have cosine of a whole pi is positive or negative. Cosine of 1 pi.
Negative.
It's negative. So I want to get a negative term when n is 1. Will this give me a negative term when n is 1? Yes. If I made that exponent be n plus 1, and I'll put it in there so I can erase it. If I let n be n plus 1, then this would give me a negative first term, but this would give me a positive first term. So that exponent doesn't need to be n plus 1, it just needs to be n.
So you need to just kind of check a number to see if they align.
Yes, exactly. All right. So this actually was an alternating series, although at first it didn't look like it. Now it looks like an alternating series where the base non-alternating part is what? So I just want the limit as n goes to infinity of 1 over n. And what's that limit? 0, and what does that tell me?
Alternating series converges.
Tells me the alternating series converges. Doesn't tell me anything about the series 1 over n, but it tells me the alternating series converges. All right. Let's just do the last one. How would you write that a sub n, the nth term of the alternating series without the negative 1 plus 1? Or negative 1 to the n plus 1? N equals 1 to infinity of n to the 1/2 over n to the 1/3. You want to clean that up any before we take the limit? What's that? 3/6 minus 2/6 is 1/6. What's the limit as n goes to infinity of n to the 1/6? We get infinitely big, and what does that tell you? Yeah. So the alternating series test is pretty easy as long as you remember to confirm that the series is alternate, or that the series is decreasing. If you don't confirm that the series is decreasing, then you really can't use the alternating series test. And let me clarify that. I'm not saying the alternating series itself is decreasing. I'm saying the series of a sub n without the alternating part. That's what has to be decreasing. Yes. Yeah. Which is a good point. Have you flipped the paper over yet, or does that just occur to you?
Just looking at the top to get rid of the negative parts of the absolute value.
Yes, and that's fixing to be very important. On the back of the page, these two guys, these two series right here, no, that wouldn't be true. Without the minus there, this is just the absolute value of that. So when you take the absolute value of an alternating series, it ceases to be an alternating series because all the terms are going to be positive. But if you show that the absolute value series is decreasing, and then you apply the nth term test, if the nth term test fails, they both diverge. If the nth term test is 0, then what does that tell you? The alternating series converges. You still don't know anything about the series a sub n until you apply some other test. All right. Cool that you came up with that notion of absolute value, Sam. Let's talk about the alternating harmonic series. Remember, a harmonic series is just a p series where p equals 1. So 1 over n all by itself is a p series, but it's a special p series where the power is 1. That special series is called a harmonic harmonic series. The alternating harmonic series would just have -1 to the n plus 1 in the numerator. And would it converge or diverge? Or how would you know that? How would you tell whether this guy converged or diverged? Huh? Use the alternating series test on the other side of the paper. That's what the alternating series test was for. So if we just took the limit as n goes to infinity of the basic series 1 over n, what's that? What's that limit? 0. And so what does that tell us about this alternating series? It converges. The alternating series converges. Next question is, does the absolute value of that converge? The absolute value of the alternating harmonic series would just be the harmonic series without the -1 to the n plus 1 in the numerator. What do we know about this p series? It diverges. That is a divergent p series with p equals 1. So here's proof of what we were saying on the previous page. Just because the alternate series converges, that doesn't tell us that the basic non-alternating series converges. As a matter of fact, this alternating series converged, but its absolute value diverged. When that happens, we say the alternating series is conditionally divergent. Conditionally convergent. When the absolute value series diverges, even though the alternating series converges by the alternate series test, then we say the alternating series, this is the alternating series. Yeah, that's the alternating series. I typed it right there. The alternating series is conditionally convergent. So we would say the alternating harmonic series is conditionally convergent because the alternating harmonic series converges, but its absolute value diverges. If both the absolute value series and the original and the alternating series converge, then we say the alternating series is absolutely convergent. They both converge, it's absolutely convergent. And then if one of them diverges, the other is automatically going to diverge. So with any alternate series, we can either say it's conditionally convergent, it's absolutely convergent, or it's divergent. That's the 3 things that can happen. That's how we're supposed to label the next 3 problems. I found what works best for me is to look at the absolute value function first. So I would look at the series n equals 1 to infinity of just 1 over n plus 3 and try to determine whether it converged. How can I determine if that converges? Compare it to a harmonic series. the reason I hesitated on that is I was thinking, man, I wish the limit of the nth term wasn't 0, and then I could just say it diverges. But the limit of the nth term is 0, so that really doesn't tell me anything about this series. I'm gonna have to use some other test. And Chase is saying, well, that's a whole lot like the harmonic series. One over n. And what do we know about this harmonic series? It diverges. So if it diverges, is this one smaller than that one? Is that a true statement? Yes. So if the bigger one, no, that's not working. If the bigger one diverges, that's really not helpful.
So
Yeah, we'll have to do something else because I'm comparing it to a divergent harmonic series, but the nth term is smaller, and I can't say if the big one diverges, the little one has to diverge. So that was a reasonable thing to try. It just wasn't helpful. Let me make a note out there. That was direct comparison. Was not useful. Yeah. Something was bugging me. It's bugging me because I misused that last night. I said because the bigger one diverges, the little one diverges, and that's just not a true statement. So I have something wrong in my notes. But let's try a limit comparison. Let's find the limit as n goes to infinity of the original series 1 over n plus 3 divided by what I'm using for comparison. What I'm using for comparison is 1 over n. So dividing by n over, or 1 over n is the same as multiplying by n over 1. What's that limit? And what does that tell us? Okay, yes, yes. This is divergent. The limit is positive and finite, and so this, how can I write that? So this one is divergent also. I was using the limit comparison test with a divergent series. I got a limit, positive and finite. That means that this one is doing the same thing this one did. Just not for the reason that I have in my notes. That didn't prove it, this proves it. All right, so the absolute value function converged. The next question is, well, how about the alternating series?
absolute value diverged, didn't it?
Yes, the absolute value function diverged. And so what about the alternating series? What does it do?
It emerges infinity, it equals 0.
Yeah. I could either say converge or diverge there. Let me change it to converge. I'm going to say by the alternating series test, the limit as n goes to infinity of 1 over n plus 1 is 0.
That's 3.
Yes, I don't know how that became a 1 all of a sudden. Since that's 0, what does that tell you? So alternate series converges because of the alternating series test. But if this one converged and its absolute value diverged, what kind of convergence is this? Yeah. Two of these problems took that long. The rest of them were pretty fast. The conditional convergence takes the longest. The reason that I started with the absolute value series first and testing it is because if the absolute value converges, then the other automatically converges. That's actually theorem 9.16 in the book. If the absolute value converges, then the alternating series also converges, and we only actually have to do one test. It's when one of those converges and the other diverges that we have to test both series separately. If one of them diverges and both of them diverge. So what happens on number 44 with the absolute value series? The limit as n goes to infinity of, actually, I want to look at the series, n equals 1 to infinity of 2n plus 3 over n plus 10. That's the absolute value series. What can you tell me about that series? It fails the nth term test. The limit as n goes to infinity of 2n plus 3 over n plus 10 isn't 0, it's 2. And so this one definitely diverges. The absolute value series absolutely diverges. What does that tell you about the alternating series? Yeah, if one diverges, they both diverge. So I'm just going to say, so both series diverge.
But the absolute value on the one above it diverged too, didn't it?
The absolute value, this is the absolute value one. Yes, it diverged. Holy crap.
That doesn't.
It just says when.
It did diverge by the nth term.
I think you have it backwards if the
It's gotta be
if the alternating series is diverges, then the absolute value diverges. But if the absolute value.
You're right. The statement right here. When the alternating series diverges, the absolute value will also diverge. The converse of that is not true. It doesn't mean that if the absolute value diverges, the alternate diverges. The converse doesn't apply. Yeah, it's just when the alternating series diverges, you can say the absolute value series diverges as well. So this, all we can say right there is that the absolute value series converged. Something's bugging me. Absolute value series converged because it failed the nth term test.
It didn't
It
fail
doesn't
the
necessarily.
stage.
because that's not how the term test works.
Cause it didn't it diverge, cause it didn't.
It only
equal zero.
fails, the nth term test only fails when it equals 0, right? So that means it
Yes.
diverges.
When the nth term test equals 0,
That's when
Mhm.
it fails.
that is when divergence happens. When it doesn't equal 0, it means no nothing.
No, that's not right.
Inverse.
What is very tongue twisting and actually brain twisting, it's not just my tongue that's twisted right now. You have to keep being very specific and saying in every case, whether you're talking about the absolute value series or the alternating series. Here, the absolute value series, this is the absolute value series because it didn't have the -1 to the n plus 1. So this is the absolute value series, and it failed the nth term test. Aaron's still saying
It
no.
doesn't fail it, it only fails it when it equals 0, right? The nth term test.
No, failed, the nth term test says if the nth term is not 0, then that series diverges. When I say fail, I'm talking about cannot use. We can't use the nth term test to say anything. The conditions fail when the limit is 0. Here the limit's not 0.
Yes, so
It's
it
not
diverges.
Yeah, it diverges.
So we know something.
Yeah, we know something, we know it diverges. But I should not have said both series diverge just because the absolute value one.
Well, the thing about this particular problem, the nth term test for the absolute value is going to be the same thing as taking the limit for the a sub n. They're the exact same. So both of them do diverge. You would just have to word it.
It's not because of this that they both diverge.
It's because-
I could say, what could I say differently? So both series diverge. I could say this one because of the nth term test, and this one because of the alternating series test.
The absolute value one doesn't diverge because of the nth term test. It diverges because of the statement above that says if the alternating series diverges, then the absolute value will also diverge.
If this one diverges,
No, that the
No, if-
alternating series diverges.
yeah, if this one diverges,
Then the absolute value will diverge. The taking the limit proves that the alternating series will diverge.
no. Well,
Yes.
that's used, but that's actually not the nth term test at that point. That's the alternate series test.
Yes.
So this one diverged by the alternate series test. This one diverged by the nth term test. Because the alternate series test says that limit has to be 0, and that limit's not 0. This limit being 0 actually applies to both of those tests, or that limit not being 0 applies to both of those tests. But it applies to the absolute value one as the nth term test. It applies to that one as the alternate series test. All right. I know. It was not difficult for me to get the right answers on these last night. It really didn't take me very long to do last night's homework and to get the right answers. I knew it was going to be difficult to explain because it's so darn wordy. You've got to be very specific about whether you're talking about the alternate series or the absolute value series in each case. I didn't get as many examples as I want to do done, and I don't feel like I was very articulate in this. I'm gonna ask that you try the homework and we can work more on it Monday. We can work on saying it better Monday. And then we do 9.6, and that's all that's on test 4. And test 4 is next Thursday. So we still got a whole week.
The 5 through 21 and 37, 53.
Yes, that is the homework.